Hello. In this video, I will introduce a general extension for NeRF models, DDNeRF, Depth Distribution Neural Radiance Fields. NeRF is a neural network model that learns the implicit representation of the radiance field of scenes. The training data is a collection of RGB images together with their camera parameters, and the task is to synthesize a novel view of the scene. NeRF achieves state-of-the-art results, but still suffers from two main drawbacks: high computational demands and decreased performance in complex scenes. DDNeRF is an extension for the existing NeRF models. It produces a more accurate representation of the density distribution along the rays. Our main contribution is allowing the use of fewer samples during training and inference, and produces better output quality, especially for complex scenes. Most NeRF models are using hierarchical sampling technique that works as follows. First, uniform samples are taken along the ray, and the model predicts the color and transparency per interval. Those transparency values are then interpreted as a discrete PDF. Second state samples are taken with respect to that PDF, and final RGB color is calculated with respect to the second state samples. DDNeRF refined the above distribution by predicting the internal Gaussian parameters for each interval. It allows DDNeRF to take more accurate second state samples, which lead to more efficient training and inference process and to better output quality. The model predicts the internal Gaussian distribution parameters for each interval. We truncate those Gaussians inside the interval bounds, ended up with one truncated Gaussian per interval. Gaussian weights are calculated with respect to the total transparency from those intervals. The final distribution is defined as a mixture of truncated Gaussians. The coarse model learns to predict the distribution by mimicking the fine model predicted distribution. We use KLA versions between those distributions and add a regularization term to avoid overshrinking of the Gaussians. The distribution estimation loss component is added to the regular NeRF loss. This is a comparison of a training process with 8 intervals between MIPNeRF and DDNeRF. Notice how DDNeRF in the second row produces more accurate distribution, which lead to more precise second state samples and to better output quality. Also, note how DDNeRF distribution keep refining through the entire training process, while MIPNeRF distribution remain relatively static from an early stage. We tested our method on various domains using different number of samples. Models who used our extension outperformed the baseline models in all cases. The most significant gap in the results was observed on complex scenes, and especially around complex geometry regions. For unbounded scenes, we integrated our model as the NeRF++ foreground model. The results have improved significantly. Thank you for listening. Our code is available on GitHub.